This is tutorial 27. Today we will end our fluid mechanics tutorial series by a discussion about lift. As mentioned in the previous video, lift is the y component of the fluid force acting on an immersed object. And in fact, the shear stress contribution is rather secondary. Usually the lift force is contributed by the pressure difference. And the lift coefficient is a function of these parameters, in which the Mach number here accounts for the compressible effect, and the Fr here is dealing with the free surface. But we are not talking about these two in this course. And surface roughness is again rather secondary, since the shear stress itself is not important anymore. By looking at this integral, we can immediately see that non-rotating symmetric object to the flow direction has zero lift. And looking at this car, usually the roof side has a higher velocity, and because for such a high velocity flow, the boundary layer is really thin, so that we can apply the Bernoulli equation between the free stream and the roof of the car, so that pressure at the roof of a car is really low, and this will produce a lift for the car. So, for non-symmetric bodies, the lift is usually contributed by such pressure difference. And for a car, usually wants to reduce the lift, so that the car is firmly riding on the roads. And of course, some shapes are more efficient in producing lift. And one shape produced lift effectively is called the airfoil. The airfoil usually takes a streamlined shape and it is installed in propellers. To describe an airfoil, we use the planform area, that is the area observed from the top, and the aspect ratio. Usually, the longer the aspect ratio, the more efficient the airfoil is. The angle of attack is the angle that the chord line makes with the flow direction. With some angle, lift is produced much more efficiently. It is because the pressure difference would be much larger. But then, at some critical angle, flow separation occurs since the airfoil starts to block the flow. And this would dramatically decrease the lift and increase the drag. And this effect is known as stall. Very dangerous in an airplane. Looking at an airplane, the takeoff usually takes really large lift since it has to carry many passengers up to the sky. A technique to increase the lift is to add flaps in the airfoil. But the cost is that the drag is also increased, so that it requires more fuel to overcome the resistance force. So a trick is that to have the flaps open during the takeoff and retract the flaps in the sky. Another thing about lift is circulation. We can use potential theory to model a viscous flow over an airfoil. Looking at the figure, this is the real case of flow. And under viscous assumption, this part is rather ridiculous. So this is our first problem of using potential flow to model flow over an airfoil. And the second problem is that if you remember from the previous tutorial, the drag and lift are both zero under viscous potential flow. But there is a way to do some corrections. It is to add an artificial vortex somewhere in the object. After doing so, we see that the streamline becomes normal again, and making a clockwise vortex will generate a lift. We will show that in the next slide. But you may ask that adding an artificial vortex is rather unreasonable and arbitrary. But this is not the case. The physical significance is that the airfoil does not have infinite length, and there are edges here. And around the edge, there is a vortex circulating like this. This is called the trailing vortex, and such vortex has the same magnitude of the artificial vortex we make to the flow, and we term the artificial vortex as the bound vortex. So, why do we have these two vortexes at the edges? If we look at the pressure distribution, the lower surface has high pressure to produce lift, and the top side has lower pressure. Air molecules always want to go from high pressure to lower pressure, So the air molecule here will migrate from the bottom to the top, and this will create a vortex. And this vortex has practical application in the nature. During seasonal migration, the migrating birds will form a V shape with its fellows, and they will fly much more efficiently and can travel a very long distance with little energy. By adding a clockwise vortex will generate a leaf. Since we have much time in this tutorial, let's waste some time and do a complete proof of this formula. And this formula appears in the lecture note, although this is not on exam. In this proof, we will make use of complex variables. If you are interested, you shall take the complex analysis math course. First, we shall retrieve the complex potential. So this comes from chapter 6. For uniform flow, these are the velocity potential and the stream function. And the complex potential is defined this way. So if we plug this in, we get F equals UZ. But we still have to add the vortex. And if we add this term here, it will look like. But since the vortex goes clockwise, we shall make a negative sign in between. And then, from this theorem out of syllabus that I have taught in the last tutorial, we can plug this in, and for analytic function, we can perform differentiation as usual as in real variables. If we expand this term, it looks like and we have another theorem from complex variable that can be used to simplify this integral. Look at our expression. It is already in the series form like this, where in complex analysis, singularity is allowed in then series expansion, and the series expansion is called the Laurent series. So this integral is just the coefficient in here times 2 pi I as mentioned in this theorem. So this cancels out. And compare the real and imaginary parts, we get the drag force equals 0, and the lift force is this guy, which is proportional to the strength of the vortex. So, by the virtue of the theorem in the last slide, we now have a method to produce lift for a symmetrical object over a uniform flow. That is, to apply some rotations on the object. If the rotation is clockwise, then the lift will be upward. If you play ball games, this concept shall be really familiar to you. And shown here is the lift and drag coefficient under this Reynolds number as V varies the angular velocity. And in the lecture notes, there is already an example about how to maintain a tennis ball in air not to fall down with rotation. So I'm not going to repeat that, and we look at some easy examples. Now the planform area is increased by 50, and the lift coefficient is increased by 30. So now we write down the expression for the lift. So these guys are held constant, and we get (28.4% decrease). And we have another easy example. If we have an airplane in glide condition and the wind is blowing this way, directly ahead of the plane, then this is the drag force and this is the lift. So if this is the glide angle, and we set our new coordinate system and do force balance along the x direction, and since the ratio of the drag force and the lift force is same as the drag coefficient versus the lift coefficient, and we retrieve the tangent theta. So this is the end of this short video about leaf, and we talk about an important asymmetrical shape called airfoil, and we discuss some leaf physics about it. Finally, we talk about the relation between circulation and leaf. And I give a final hint to you guys for the final exam. This is rather rubbish, but what I can say about the exam is that please get prepared about Chapter 6 and Chapter 8. Only about 10 marks will be allocated to Chapter 9. It's because there is really not much things that professor can ask you about, especially the calculation problems in this chapter are too easy to test you guys. And last but not least, you must not forget anything before the midterm. You are really familiar with balloon equation, but concepts about hydrostatic pressure and streamline can be on your final. So this is the end of the whole tutorial series, and thanks for watching throughout. Ask us any problems about the final and give us any feedbacks in the comments.